All right, so far, what we have studied, right? If you look at or zoom out at our overall learning of embedded system design, we started understanding the fundamentals of embedded system design, and we saw, okay, we need to have hardware, we need to have software, right? And we want to communicate with other devices outside that microcontroller, that is our hardware. So we started with our AVR microcontrollers. We understand input and output, right? Then we understand some of the features like timers and interrupts. And there are a few more features that we'll explore. We say, okay, now let us wait for a minute and let us connect few things that we see in everyday life to that microcontroller. When we are building embedded system design, we have displays and we have inputs, right? So displays can be in the form of 7-segment LEDs. Displays can be in form of LCDs, right? And the input can be in many ways, right? Here we'll go for 4x4 keyboard. That is one of the examples, easy to understand for us, right? So now we say we understand some of the concepts of our AVR microcontrollers. Now let us utilize our learning to interact with the outside world, right? So that is the big picture. And then we may come back to some of the internal features. And remember, we'll be doing all these experiments in the lab as well, right? Probably starting from experiment set 4, then we start exploring 7-segment LEDs and probably LCDs and so forth, right? So what we study, we will implement in the lab as well. So with that, let us understand the concept of 7-segment LEDs. Where do we see 7-segment LEDs? Any quick example in the real life? Everyone? Okay.
Wall clock.
In the?
Wall clock.
Yes, wall clocks. Wall clocks has 7-segment LEDs. Yes. Good point. Any other place where you see 7-segment? Okay, lift. Yes, in the lift, many times we frequently see the 7-segment LED displaying few things. Fine. What else? What are other possible applications when we see that display? Okay. Do we see similar scenarios at traffic signals? May not be exactly identical 7-segment we use in the lab, but maybe the bigger version or better version, right? At the traffic lights. And do you see the counting down of the seconds? Wait for this many seconds, right, before you drive. Yes or no? That is 7-segment LEDs. Maybe say other examples, right? Maybe on washing machines, you may see some of the times, right? Generally it counts in minutes. These many minutes remaining, right? Microwave ovens, maybe when you're dialing in that, okay, I want to maybe hit up something for this many seconds, right? Maybe you may see these displays, right? So we will understand, we will explore this. And in a way we understand them because we understand LEDs. This is this combination of LEDs. So, yeah, mid-sem exam we discussed, right? That was our quick revision. We go to 7-segment LEDs. So here is the fundamental. We go back to our high school, probably physics, that, okay, we have Bohr's model for simple atoms, right? And the fundamental thing is, okay, we have nucleus and around that we have electron. This is quite simplified version of atom, okay? It is quantum mechanics and many more, say, deeper sciences, right? Here it is simplified version. We have circles and this. So we say, okay, we move away from the nucleus, the energy of electron increases. And when electrons jump from higher energy level to the lower energy level, it will emit energy. And that energy can be in form of radiation, right? So delta E here is the difference of energy between, say, third orbit and second orbit. And that energy is emitted in terms of some frequency, right? H is constant, F is the frequency. Now, if that frequency happens to be within the range of visible light, we can see that, right? So this is the fundamental. Now this is for atoms. Now LEDs are made up of semiconductors. So things are different. So here is a quick diagram of LEDs, right? You can see this left-hand side diagram. Can you see my cursor? Yes or no? I'm moving the cursor.
Yes, sir.
Yeah. So here, see, these are semiconductors. The previous diagram was very simple. Say hydrogen atom, for example, orbits. Now here we have bands, right? And the topmost band we may say the conduction band, right? This is topmost band, and you move up in the y-axis. We have higher energy. You move down, We have lower energy. So we have conduction band, then we have valence band, and below that there will be inner orbitals. And if you move down all the way on the y-axis, we may have nucleus, for example. Right? So moving up higher in the energy. All right. So when electron jumps from the conduction band to valence band, it may emit the radiation. And what is that energy? That is the energy difference between the conduction band and valence band, roughly speaking. Right? So depending upon this band gap, the energy and hence the light and the color of that photon will be determined. And hence to do that, on the right hand side, we have a list of semiconductors and the colors they emit. Right? So suppose, say, look at the first one, gallium arsenide phosphide. So now if you have this combination of gallium arsenide and phosphide, the band gap will be such that when electron jumps from conduction band to valence band, the energy will be equivalent of this. Right? The peak, the energy will be around this micrometer, and it will emit red color. And you can go down in the list, different semiconductors and different colors, because this band gap is different. Right? We can carefully engineer the band gap depending upon the combinations of these semiconductors. Right? So on the left-hand bottom, we have the LEDs are typically made up of compound semiconductors, and they are of direct band gap. Direct band gap means, okay, a little bit technical, but for our understanding of electron can easily jump from conduction band to valence band. All right. So this is how the atomic model is different compared to the semiconductors, because in semiconductors we encounter bands and we can adjust the band gap by different combinations of semiconductors, and here we have our LEDs. All right. So now we have LEDs, we want to connect with our controller. And generally there are two ways or two approaches when you connect LED to IO pins of microcontroller. One is the LED cathode are grounded, and logic 1 from the IO pin will turn on the LED. In this case, we are connecting the anode to the IO pin. Here we supply the current, right, by the IO port. So we call current sourcing. The other method is LED anodes are connected to VCCs and the cathodes are connected to the input output pins. Here, what happens is anode is connected to VCC. So logic 0 from the IO pins will turn on the LED. The current is, in this case, provided by the power source. So our IO pins will sink the current. So we call this current sinking. All right. And someone may say, okay, I want to have one pin, say anode connected to one IO pin, cathode connected to another IO pin. Okay. This is also a possible combination. You try this in the lab and see how you can turn on that LED. All right. But in that case, you utilize 2 pins of IO ports. Right? Sometimes number of pins may matter, right, depending on the functions. So this is widely used way. Now this is LED, and you are expert of LEDs at this stage. You have been working with the LEDs in the lab. Now we extend to 7-segment LED. It is just an arrangement in space. Same concepts apply, just arrangements in space. Okay, so here is what we call 7-segment common anode. So look at the diagram on the right hand bottom. This is, I think, our familiar diagram of 7-segment LEDs. We label them as A, B, C, D, E, F, G, and we have decimal point here. All right. And if you look at the circuit diagram, it may look something like this. It is common anode. So anodes connected to power supply. So here you see these are the diodes and connected to power supplies. In this case, plus 5 volt. The cathode is connected to data lines. So all data lines individually, say D0, D1, all the way to D7. Right? The port pins, we connect them, and logic 0 turns on segment. So now here is an example that suppose we want to display digit 1 on this right side bottom 7-segment LED. What I need to do? Turn on segment B and segment C. Okay, B and C. Now in this case, right, if I provide logic 0 to B and C and at other places logic 1, assume that is equivalent to power supply. Right? 2 of them are forward bias, they will turn on, and we will display logic 1. Is it clear or not? Right? So suppose I want to display, say, digit 3. Okay, digit 3. Then which segment I want to turn on? Can you type? on the chat box. I want to display digit 3 with this configuration, digit 3. Can you type which segment should I turn on? That is first question. All right, I am waiting for your answers. Okay, we have a few answers. A, B, C, D, and G. That's correct. Right? A, B, C, D, and G. These are the segments you want to turn on. Now to turn on these 5 segments, assume that you have connected this LED, 7-segment LED to any port. These are 8-bit ports. So what number will you send to that port? You can type in binary to simplify things. Okay, you have diagram before you. Can you type in binary, right? All 8 bits, which 8 bits you will send out to turn on 3? Everyone, can you type please? Right. So remember logic 0 will, so in this case, what happens? Logic 0 will turn on the LED. So let us see, do you want to turn on A? Right? And depending upon say A is in this configuration is connected to the LSB. Right? So D0 will be logic 0. B is connected to D1, right? You see this matching. So that will be logic 0. C is connected to D2, logic 0. D is connected to D3, that is logic 0. All right. And G is also should be turned on. So G is connected to D6. So you see that we need to have 1 0 1 1 0 0 0 0 combination. So many of you are perfect in answering 1 0 1 1 0 0 0 0. If we talk from MSB to LSB, everyone gets this or not?
Sir, why is the logic inverted? Is it because anode is connected to VCC?
Yes, anode is connected to VCC, and you are connecting the cathode to the port
lines.
Right. So now, if you want to forward bias the LED, right, anodes are at +5 volt, the cathode should be at 0 volt. So there is a +5 volt, right? So forward bias the LED, then it turns on. All right.
Yes,
so this
sir.
can be one configuration. And now, see, remember that there is no 1-to-1 match. Okay. Logic, say if you write down 0 1 hex, that will not turn on the 1 when we display that. When we say 02 hex, it is not going to turn on 2 on display, right? So there is no direct match. We need to make sure that we have the right combination of bits to turn on things. Yeah. Fine. Now, there can be second scenario, that is common cathode. Okay, common cathode, you can see the diagram. All the cathodes are connected to ground. And now on the anodes, we have connection to the IO pins. So common cathode scenario, cathode is connected to ground, anodes connected to data lines that are pins, and logic 1 turns on the segment. So here is an example. To turn on, say, digit 1, in this case, all segment except B and C should be off. So in this case, right, when we send logic 1 to B and C, so these are here B and C, that is 1, that is 06 hash, H will display digit 1. This is second configuration. All right. So now in this case, let us see. I want to display 5. Okay, I want to display 5. Which segment I want to turn on, first of all? Can you quickly type on the chat box? I want to display 5. Which segments should be on? What do you think? In this configuration. Everyone, can you think? 5, so A, F, G, C, D. Correct, right? So most of us are getting this, right? And you can change the sequence, right, as you want. The thing is, yeah, A, F, G, C, and D should be on. Right? And to do that, what should be my 8-bit message that is going out on the port? Now I want to write down the, say, binary. What should be the 0s and 1 going to the port? In this case, to turn on these segments. Remember, to turn on, you want to send logic 1 there. Okay, turn on, you want to send logic 1. And assume this configuration, right? A is connected to D0, so A is connected to the LSB, least significant bit, and we move forward, G is D6, and decimal point is same as B, all right? So we have 0, 1, 1, 0, 1, 1, 0, 1. Now, is it correct, everyone? Okay, decimal point is off. Then what happens? F and G, right? G is on, right? F is on, E is not on, D is on, C is on, and A is on. So do we get this point or not? So we need to have a carefully written say code if you want to display these numbers on 7-segment LEDs. And in the lab, we will do the experiment. Okay, can you count down from 9 all the way to 0, right? On single LED, 7-segment LED, first to begin with. First experiment can be that a countdown. So you will see very similar thing that is happening with one 7-segment LED only, right? One digit LED display, counting down from 9 to 0 with some time delay between them so that we can perceive that easily. All right. So I believe you can do that. So that is one scenario. Okay. So here is the question. And question is, assume that one common cathode 7-segment LED is connected to port A of AVR microcontroller. One enable pin, active high of 7-segment LED is connected to pin 0 port B. Write a C program to display A on this 7-segment LED continuously. So can you note down this question? And yeah, when we meet probably for the 4th lab, we will explore this in the lab. And I think you can do this easily. Yes or no? To display A, right? To display A, which segment should on? In this case, if it is common cathode, right? Common cathode, I think you have done that. Common cathode. So if you go back, this is common cathode, and I want to display A, right? So you can figure out. So EFA, BC, let us check. So EFA, BC, G, right? Do you want to turn on G as well to display A? Right, Kashish? Right. So everyone gets it, right? Only D is off, other things are on. We assume that is A, very much similar to A. Everyone gets this, right? So such questions, yeah, we'll begin with simple one, and then here is the question, right? And then we will go to the next question like this. Assume that one common anode, in this case, we change the type of LED, 7-segment LED. One common anode 7-segment LED is connected to port A of AVR controller. One enable pin of 7-segment LED is connected to pin 0 port B. Now, write C program to display 9 to 0 on this 7-segment LED with delay of 1 second between each number. So again, I think this would be a good candidate to run in the lab, right? Would be part of experiment set 4, right? And would be interesting. You can see, yes, this is what we see on traffic lights and many of the scenarios, right? When we count down the time. Maybe you can have 1 second delay. So yeah, this will be the thing we'll take. So you understand the overall logic, right? We will send out the number, right? So starting with, we send out the combination of zeros and 1 to display 9, wait for a second, then send out the combination to display 8, wait for a second, 7, wait for a second, all the way to 0, then we can roll over if we want. So is this question doable? Everybody? Right, and I think in the lab you will see this very clearly and vividly. Right, so that is good. Now the only thing is, can we extend this? So I'm taking this picture from this website mentioned on the right hand side bottom. So yeah, can we connect many of them in say combination? Answer is yes. Right, here is example of Arduino. Similar situation with our AVR controllers. Right. That okay, we put say in this case 4 of them in parallel. We may control each one individually. So we have 4 of these, 1, 2, 3, 4. We have separate control bit, right? And then we can share our data lines with all the LEDs, and we can do the programming of multiple of them, right? So this is control to turn on the LED. All right, and again we will run this experiment in the lab with probably 2 at least Now 4 can be a little bit more connections. We'll try to run 2, and maybe we can display some counting of time or countdown like our traffic signal and so forth. Okay, so this is extension. And if you go back to our questions, right, there is one enable pin is involved, right? That enable pin will activate that 7-segment LED. All right. So that one enable pin, right, is designated here on the right hand side. That okay, for 4 of them, 1, 2, 3, 4, we have one enable pin, and that we control through other IO pin. And in this case, it is Arduino. We have more facilities. We have 4 ports with 8-bit parallel IO ability, so it will be much better, right? So yeah, this is, I think, again, the program would be more efficient and more say vivid to do in the lab, right? So combination of 7-segment LEDs. Any questions at this stage? Any questions?